At this point, I've made a few videos to get our Real Analysis 1 course going. I wanted to stop for just a moment to discuss 3 results that I actually have in the Logic and Proofwriting playlist. If you haven't seen that yet, you may want to go back and look at Logic and Proofwriting before continuing in Real Analysis 1. So that's a pretty short playlist where I just have a few videos, like a handful of videos, covering the techniques of proofwriting, which is critically important when you study real analysis. We write a ton of proofs together. And then also I have these first 3 results, which are fundamental, and especially the first 2 frequently used in the study of real analysis. So I'm not going to prove these results again, although they would happen typically in the first week of a real analysis course. They were done in this playlist. So I've already recorded them. You can go back and watch them. It is important to know both proofwriting and some of the results in those videos. The first one is the triangle inequality. So for any real numbers a and b, the size of a plus b is less than or equal to the size of a plus the size of b. Or in other words, the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. This inequality here will be used all the time. It is an extremely useful technique when we write proofs in real analysis. We will often say this is going to be a triangle inequality argument. Going along with that, in fact, I probably should have put result 2 above result 1 just to emphasize the importance of this idea of taking the absolute value of a quantity. In real analysis, we will often want to show that 2 expressions, 2 quantities, 2 ideas are the same. So what we may want to show is something like a equals b, but actually writing down hard equality with this equal sign is not tractable. So instead, what we show is the right-hand side of this if and only if expression that I have here in my second statement. Instead of showing a equals b directly, what we do instead is we'll say, let epsilon be some arbitrarily small number. And then for any such choice of epsilon that we could make, we can show that the distance between a and b is less than, or sorry, just less than. You could say less than or equal to, but the statement's going to be less than that number epsilon. So you want to think of, let me use this one, the absolute value of a minus b as like the distance between a and b. So to show that a and b must be the same notion, the same measurement, what we will show is that the distance between them is less than any positive number that we could put. So that's often how we get to equality in real analysis. And therefore, we have to work with this kind of expression a lot with absolute values, and therefore, we often bring in the triangle inequality. The third result is not as prevalent in real analysis as the first 2. These are techniques that we will see all the time. The third one is just a very famous statement, and that is that the square root of 2 is irrational. It's a famous proof by contradiction. There's a lot that you could say about the historical importance of this result. We talked about rational numbers already. Rational numbers are ones which can be written as ratios of integers. So 3/7, you can just say that. That's a rational number. It exists. How do I even know that there are irrational numbers? Typically, you start with this result. So you say, hey, look, here's a number which cannot be expressed as a ratio of integers. Therefore, it is not rational. That tells us that there must be numbers out there which cannot be written as this ratio of integers. So there's another type of number. And that result, we think, was discovered a long time ago, thousands of years ago, by the Greek mathematician Hippasus, I believe, if I'm saying his name correctly. And he was in the school of Pythagoreans. And the historical legend is that they got so excited about this result that there could be a number out there that was not rational, that they had a boat party. They took him out and drowned him at sea, actually, because, in fact, it was disturbing. Before I say more about the square root of 2, let me just move on to the result that we will prove in just a moment. So this is going to be the only result in this lecture. That square roots actually exist. So if you think back to the square root of 2 is irrational, you could say, wait, how do I even know that there is a number whose square is 2? And going back to the Pythagorean theorem, I can just immediately justify it to you. If you take any right triangle whose side lengths are the same, so an isosceles right triangle, if this side is 1 unit and this side is 1 unit, by the Pythagorean theorem, which of course does not need this result, that's a geometric proof, you know that the measurement you have to associate to the hypotenuse would be the square root of 2. So that number does exist. there is a number out there whose square is 2. How do I know that there's a number whose square is 5 or whose square is 11.7? Any kind of real number which is positive. We've always taken for granted, perhaps, that we can just do the square root of a number in our calculator and we get a result. We don't get something like, hey, there's no such thing. But I would like to prove for you, because it must be shown, that, in fact, in general, square roots do exist. So not just the square root of 2, but the square root of any positive number is a number. Okay, so I color-coded it here. These are all results that I've proved previously in earlier videos. This is what we're going to do in just a moment. I will come back in a minute and we will set up this demonstration. So here's the result that we would like to show. Given any non-negative number c, there's another non-negative number out there, r, which, when squared, returns you back c. So that is the definition of saying that r is the square root of c. You may be thinking, well, negative r would also square to c, and yes, that's true, but the square root of c is a non-negative number. Let me just quickly point that out, because this is a mistake I see students make. I think it's because of the way that we sing the quadratic formula. The square root of 9 is not plus or minus 3, it's just 3. Okay, 3 squared is 9, negative 3 squared is also 9, but the square root of 9 is 3. When we draw the square root function, we draw it in the first quadrant. Okay, so what we're going to do is fix c in our proof, and then I have to somehow create this number r. We are going to create r as it relates to a set. So let me just pause for a moment and I'll erase this. I want to create a set of numbers whose supremum is actually going to end up being this number r. So given just that piece of information, maybe sketch the number line, think, what could the set A look like? And if you have no idea what I'm talking about, that's fine. I'll come back in just a moment. Here's the set A that we are going to need. So proof. Let A be a set of real numbers. And I'm going to be looking at non-negative numbers. It's going to be all of the real numbers x, such that x squared is less than c. So I don't know if there's a number yet whose square is c, but certainly 0 squared is less than c. So this set is non-empty. And it's bounded below by 0, because we're looking at non-negative numbers only. Let me take a moment to justify to you that A is bounded above. Probably believe it right away just from this inequality, but at this stage in Real Analysis 1, it's useful to work through the details. We're really building up our understanding of the real number line. So our first result is that A is bounded above. We can use the Archimedean principle. By the AP, there exists a natural number n which is bigger than c. So I'll write there exists a natural number n such that n is greater than c. Consequently, n squared is greater than n. It's probably strictly greater, but if n were 1, I would need that. So greater than or equal to n, greater than c, greater than x squared for all x in A. Comparing the left side and the right side, n is greater than x. There I'm using order axioms for the real numbers. N is greater than x, so n is an upper bound for A. So n is an upper bound for A. Let me pause right here. We know the set A is bounded above, and therefore by the supremum property, it will have a least upper bound, or in other words, a set supremum. I will come back in just a moment to write that down. I will erase this proof of boundedness. It's not the most interesting part of this problem. So go ahead and copy this down, and then we can continue. Picking up where we left off, I erased some of the proof here, but let me write the conclusion. By the supremum property, so by the supremum property, which I will abbreviate like that, there exists a number r equal to the sup of A. I never like using the letter from the statement without kind of alerting the reader to that fact. So let me add here, we will show that r squared is C. Okay, so it's like I'm already kind of stating the conclusion by using the letter R, but let me point out to you that we haven't done the work yet. We still need to show that R squared is actually C. Here it's going to be an argument using the three different possibilities that two numbers can relate to each other with on the number line. So this is one of the order axioms. Either case one, R squared is less than C, or R squared is greater than C, or if it's neither of those, R squared equals C. What we are about to do is show this can't happen and this can't happen. That allows us to conclude that the set supremum that we just wrote down is in fact the square root of C. Okay, let me show you how we will tackle both of these just with a picture, and then we'll write down the details. Let's say C is here, and for the first situation, R squared is to the left of C. So there's some measurable distance between these two numbers. Let's say R squared is here. So maybe R is back here. What I want to do is build a number that's a little bit bigger than R. So we're going to find some number here. And with algebra show that when you square it, it lands in here. So then we will have a number whose square, let's say, I think we're going to write it down as something like R plus 1 over n. So I'll go ahead and give it that form. And this is going to be its square. We will have a number whose square is less than C, but that number is larger than what we claim to be an upper bound for the set of numbers whose square is less than C. So this construction will show us that R cannot even be an upper bound. So that will be the goal for the first case. Build a number slightly larger than R whose square is still less than C, because we have some room here. Algebraically, we're going to be able to squeeze that square in this gap between R squared and C. And then we'll be able to contradict the fact that R was ever an upper bound to begin with. On the other side, let me switch to pink. If R squared is bigger than C, let's say this is R squared. Again, going back to the original number R, maybe now it's here. Or actually, let me just leave it here. Say this is R. In the case where we have some distance to the right of C, what I'm going to do is take a little off of R. I believe in our proof we'll write this as R plus 1 over capital M, where you'll see what that looks like explicitly when we write down the proof. What I want to do, minus, we got to subtract off to the left. We'll move a little bit to the left of R, square that number, and algebraically show it lands in here. Therefore, it's also an upper bound for the set A, but it's smaller than R squared, smaller than R squared. It's smaller than R, that's what I'm trying to say. It's smaller than R, therefore, R is not the least upper bound. So here, our goal will be to show that R is not even an upper bound at all. And here, we'll say, hey, it's an upper bound, but it's not the smallest upper bound. So we'll have two different routes to contradiction. After doing that, we'll be able to say, you know what, they must actually be equal to each other. So R squared is C. In other words, R is what we will think of as the square root of C. Okay, I got a little turned around with my picture. What I'm going to do, though, is explicitly write out the computations for both of these two cases that we need to work through. Let me do that in just a moment. We'll work through this one and then the second one as well. And then we'll be done with this video. I erased the statement laying out the three cases for you to give myself more room, but we're going to jump right into that first case. Imagine that r squared is less than c. What I'm going to do with this first case is just write up what happens. I will try to show you at the end constructively how I got the term that I'm going to introduce in. And then after we've had that discussion, we will do the second one in a more brainstorming way so that you'll see the thought process that went into picking the natural number that I'm about to design for you. So if r squared is less than c, by the Archimedean principle, there exists capital N from the set of natural numbers so that its reciprocal, 1 over n, is less than c minus r squared divided by 2r plus 1. Okay, so this is the thing. I'm just going to give it to you right now and show you that it works. Then I'll show you how I got this. And then for the second case, I'll let you think about what needs to go here. Okay, what I'm going to do is take this number 1 over n and add it to r. Before I do that, let me quickly justify that this number 1 over n does exist. So if r squared is less than c, c minus r squared is positive. 2r plus 1 is positive. So we have this positive number here. By the Archimedean principle version 2 that we saw in the previous video, there is such a natural number n whose reciprocal is less than this positive number. Okay, observe. R plus 1 over n squared. So I'm moving a little bit to the right of the number r. Let's expand this out. R squared plus 2r over n plus 1 over n squared. Often in analysis, you start doing estimates where you go up or down in size. I'm almost always looking to go up in size. So here, my thought process algebraically is if I make the denominator smaller, I make the fraction bigger. I'm going to take this 1 over n squared and replace it with 1 over n, which takes me up in size. And then the whole reason I did that is it's easy to add these two together. Let me now drop down a line. So I will say that this is equal to r squared plus 2r plus 1 over n. And then look at how we chose the number n. If I were to bring 2r plus 1 over here, 2r plus 1 divided by n is less than c minus r squared. So we have that this is less than r squared plus c minus r squared, which is c. Sorry about this horrible formatting. But what have we now shown? R plus 1 over n, that quantity squared, is less than c, which means that this number belongs to the set A. Thus, the number r is less than r plus 1 over n, but r plus 1 over n is an element of A, which means that this number cannot be an upper bound of A. And that contradicts our assumption that r was the supremum of A. That's what we set r to be equal to. So we're saying now that it can't be the case that r squared is less than c, handling case 1 for us. Obviously, in a moment, I will erase from here to the end, but before we do that, let me kind of tell you that often you understand that you want to do this. You want to take a number and just tweak it a little bit, and that amount that you change it by is often expressed as something like 1 over a natural number. These terms 1 over n just give us a lot of control to kind of zoom in around a fixed number. So here I want to take r and just perturb it a little bit. So I'm going to move a little bit left and right. Here I'm moving to the right. So this is like a great thing to add to the number r to just move us a little bit right on the number line in a way that I can control the size by the Archimedean principle. Then I just do some algebra. Again, with analysis, you're often looking to remove excess terms to kind of get to a nice clean expression. So while we could have perhaps stayed with this expression as it was written, realizing that 1 over n squared is less than or equal to 1 over n means that I can just kind of knock out that squared term and go up in size. And that's okay because I'm trying to show that I'm less than c. So if I can get this less than c, we're still good with our original expression. And then that was a nice clean thing that we could combine. So we got this. Now here, at this point, this is where I realize, like, I would like for this to be less than C. So working this out on scrap paper, you would take this and set it less than C and solve for n. So, sorry, I'm kind of overlapping my writing, but on scrap paper, you might not have had this at the beginning. You could say, I know that 1 over n can be made arbitrarily small, but I don't know how small it will need to be in the actual proof. Let me take the proof as far as I can go without that knowledge. And then you say here, and I want this to be less than C, and now solve for n, and you'll get this. So C minus r squared brings that over, divide by the 2r plus 1. Make sure that this is positive at the end, so you're using the Archimedean principle legally. It is, so we were good to go. Okay, so this is what you do first, and then you write this down with a lot of confidence before all the algebra comes. Everything cleanly checks out. All right, let's move on to case 2. And for case 2, what I'm going to do is start with the same opening, but I won't yet know what this right-hand side is. We will work it out together. The second case is similar to the first one in terms of the setup, so I've left up a lot of the writing here. But for case 2, we want to see what we can do in the situation where r squared is greater than c. Again, if you remember the goal with that number line that I drew, what we would like to do is take r and slide a little bit to the left to a number which we can show is also an upper bound of the set A. So the number that we want to create by taking r and sliding a little bit to the left will be an upper bound for A, which means that r could not be the sup. It's an upper bound, but it's not the least upper bound. So again, in both of these, the idea is to take r and slide a little bit to the left or right, depending on the case. And this idea of sliding a little bit on the number line can be captured by subtracting from a number, adding to a number, 1 over a natural number. The reason why is we have the nice Archimedean principle to allow us immediately to control how we choose such a natural number. Okay, so that was overview. In detail, if r squared is greater than c, by the Archimedean principle, there exists some natural number m, so that the reciprocal, 1 over m, is less than a bound that we will create together in just a moment to allow the algebra to give us what we need. So it's like we don't yet know what m is going to satisfy, but we know what we want to do with 1 over m. We're going to subtract it off of r. Let's square this as we did before. R squared minus 2r over m plus 1 over m squared. I want that to be greater than c, so that it's also an upper bound for A, the set A. If you stick with this inequality the way that it's written, it's a little bit trickier than the first one because you've got differing signs here. So if you start trying to knock out terms or combine these fractions, it's a little bit harder to do than case 1. You want to be careful that you don't maybe make one term go down in size and another one go up in size, and you lose the control over the direction of the inequality. I also don't want to work with square terms because we're trying to establish the existence of square roots. So it's like, I don't want to use anything about square roots yet. So let's see what we can do with this. If this expression is bigger than c, perhaps I could actually make it bigger than c plus 1 over m squared. If it were bigger than c plus 1 over m squared, then yes, that would be bigger than c. So it's like instead of getting to c on the right-hand side immediately, maybe I can get to c plus 1 over m squared, which allows me to conclude that it's bigger than c. Now this is nice because I just want to show that these first two terms, r squared minus 2r over m, can be bigger than c for the right choice of m. And then the 1 over m squared, that's just a number. So let's see what we need to do here. Let me do negative 2r over m greater than c minus r squared. So I will divide both sides by negative 2r. That's a negative number. So 1 over m will be less than c minus r squared over negative 2r. I think the negative down here in the denominator is kind of ugly. So let me multiply the top and bottom both by negative 1. We'll have negative c plus r squared over 2r. Let me write that here as r squared minus c over 2r. Always take a moment just to check the sign of what you just wrote down. R squared is greater than C, so R squared minus C is positive. We are working not in this first case, so C and R are both positive numbers. The denominator is also positive, so this is a positive number. By the Archimedean principle, there is such a natural number m so that this bound can be established. So down in our proof, when we start here, we can say that this quantity is bigger than C. The 1 over m squared just carries over. C plus 1 over m squared is a number larger than C. So we are done. Let me just erase this. All right, to wrap this up, let's just add one more sentence telling the reader what the contradiction is. But now, R minus 1 over m less than R, the supremum of the set A. This number on the left is also an upper bound. And that makes no sense at all, because R is supposed to be the least upper bound. There shouldn't be any number to the left, which is also an upper bound, but we found one. It wasn't case 1, it wasn't case 2. We don't need to prove that it's case 3 because of trichotomy. So let's just move on now to the conclusion. Thus, I'm about to write R, but I did a little too quickly. Thus, R squared equals C. That's what we wanted to show, that given this number C greater than 0 in this argument, there is a number out there whose square is that number. The existence of R comes from the supremum property. So here's where I said that R actually existed as a real number. It's because we know that sups exist. So since the set A is bounded above, it must have a least upper bound. That number exists. So this R exists, and its square is C. That's how we define the square root of C. So this notation here means the non-negative number whose square returns you back what's inside the square root. Okay. All right. So if you have any positive number and you take the square root, that square root exists. There's a real number out there, which when squared returns you back your original number. And that is something that you may have taken for granted for several years now. But, looking at the number line, we take a lot for granted coming into real analysis. And what we're trying to do now is construct all of the numbers whose existence we may have never called into question just because we've been working with calculators and things like that. We know that there were integers. We count them on our fingers. There are rational numbers. And now we're saying that there are also square roots of any number that you already know exist. We will wrap this up here, but we're going to continue our study of the real number line. Thank you for your attention.